Our next problem is again a very interesting problem. We are given that if 3 squares are being chosen in a chessboard, then we need to find the probability that these 3 squares are lying in a diagonal line. So for solving this problem, let us make the chessboard. Now we are choosing 3 squares out of these 64 squares in a chessboard, and we need to find the probability that they are lying in a diagonal line. So let us mark these 4 vertex as A, B, C and D. Now let us split the entire square into 2 separate triangles ABD and BCD. The different diagonal lines are as follows. Hence we can see that this diagonal line contain only 2 squares, so 3 squares will come only if we start selecting the squares which are lying after this diagonal line. So the diagonal lines which are providing us 3 squares are this, then this, this, this and this. We will not include this, or rather we would include this diagonal line in 2 separate triangles. The triangle ABD and BCD, analyzed differently, are having the common line BD. So we have to be careful in the case of line BD. So let us first separate the line BD from the entire problem and solve the question for the remaining diagonal lines. Here we can select 3 squares in 3C3 ways because there are only 3 squares present. Here we can have 4 squares, so 3 squares can be selected in 4C3 ways. Here out of these 5, 3 squares can be selected in 5C3, similarly 6C3, and the line which is next to the diagonal line BD is having 7 squares, so 7C3. Hence this 3C3 plus 4C3 plus 5C3 plus 6C3 plus 7C3 is the total number of squares, or the total number of ways in which 3 squares can be selected from this line, this diagonal line, and up to the diagonal line which is next to the diagonal line BD. Remember, we have not included the diagonal line BD. Similar number of ways can again come from the triangle BCD if we consider all the diagonal lines till the diagonal line which is next to BD. We have not considered the line BD also. So this is equal to 2 times these many cases, 3C3 plus 4C3 up till 7C3. Now we can include the diagonal line BD. Earlier we didn't include the diagonal line BD because if we would have considered the diagonal line BD in the triangle ABD, it would have again come in the triangle in BCD. So we would have got confused and multiplied this 8C3 also by a factor of 2. But this is not correct because this diagonal line BD has to be included only once, and hence now we can include this diagonal line BD, and the total number of squares present in this diagonal are 8 and we have to select 3, so 8C3. Similarly, we could join A and C and consider these diagonals also. By symmetry, the number of ways will be again equal to the number of ways which we found by splitting the triangle, or rather the square, in triangles ABD and BCD. So this is equal to 2 times. These are the total number of favorable cases in which 3 squares which are being chosen are lying on the diagonal line, divided by the total number of ways in which 3 squares can be chosen in a chessboard is 64C3, because there are total number of 64 squares in a chessboard and we need to select 3 squares, so total number of ways are 64C3. And on solving all this, our final probability comes out to be equal to 7 upon 744. Now, although this question appeared to be a simple problem, but most of the students commit the mistake of including this diagonal line BD in both the triangles ABD as well as BCD. So just be careful in this part. This question is very easily solved by splitting the entire square into the two triangles ABD and BCD, and then analyzing each of the diagonal and the squares present on these diagonals, and hence our final answer is 7 upon 744, which is our final answer.